Siri uses a number of knowledge services, and one of them is Wolfram Alpha. How many of you are familiar with Wolfram Alpha? How many of you are familiar with Mathematica? Yeah, so Stephen Wolfram is a great guy, and he produced this system, and it basically curates computable knowledge and provides amazing scientific and mathematical knowledge services to those of you who can use Siri or Wolfram Alpha directly on the web. This system has been produced by Google. It's called Google Now, and it's their answer to Siri. It exploits what Peter Norvig, the director of research at Google, calls the unreasonable power of massive data. So Google Now gives you a tremendous boost over what you would have with your unaugmented brain, because it's exploiting the billions of data points that Google has at its disposal. And the monocle over there is called Google Glass, or Project Glass, and it was produced by Google X, a research division at Google, and it provides a monocle access to augmentation systems, either a Google Now-like system and or a system that allows you to see in augmented reality as you look out on the world, a metadata enhanced view of the world. This is a robot called Robotics from Hanson Robotics. It has 33 degrees of freedom. It has something very similar to synthetic skin. It can emulate 32 different facial expressions. It's really quite extraordinary. And again, just the beginning. This is a system called the Now robot, or the Neo robot. And this system has taken over the international RoboCup soccer competitions that are held every year at the annual AI conference. That position, that vaunted position, was held by the Sony Aibo dog for over a decade. And now we have human-like robots playing soccer. And they can communicate with each other. They know soccer strategy. They have Wi-Fi. And they can say, "I'm open, shoot me the ball." So they're really extraordinary robot players. If you haven't seen them in action, you should take a look at them. I'm sure there are clips on the web. This is a very new robot. It came out this year, just actually a few months ago. This is Baxter. This is a system that was produced by Rodney Brooks. That's Rodney right there. And Baxter is basically bolted onto a work surface, and for $22,000, it provides you with industrial robotics capability. That is about an order of magnitude less than what it's been before. This system can be taught new tasks. It can multitask, and it can be taught new tasks in about less than 30 minutes or so, which is really extraordinary. And of course, these drones can be autonomous or non-autonomous. They can be fitted out with GPS. And instead of being hunter-killer drones, they can deliver medicine in very remote areas, or they can deliver packages of various kinds in places where there are no roads. We also see AI embedded in robotics in a variety of different applications. Up here, we see the Neo robot in action on the soccer field. You see CMU's system here in the Urban Challenge, the DARPA Urban Challenge. This is Peter Diamandis from XPRIZE and myself getting out of the Google robot car, an autonomous self-driving car. We had just taken a trip at 100 kilometers per hour on the highways around Palo Alto and Mountain View, California. And I just felt completely relaxed. Peter and I were just talking as if, a human driving in front of us. So the thing about this, well, we'll get back to this in a minute, but the thing about this is that it really will become the norm very soon, surprisingly soon. And this is the PR2 robot from Willow Garage, an extraordinarily capable robot, plugging itself in. So a couple of words about the Google self-driving car. that has low-level AI in it, not super sophisticated AI, just sort of horse sense to get around and to avoid objects and people and navigate around. It does a remarkably good job. And what you find is, when you actually have been in the back of one of these, you wonder, what were we thinking, having people drive? I mean, we are really not good at this at all, even if you like driving sports cars. People have poor attention spans. They get distracted by people in the car, by their cell phones, by texting while driving, drinking while driving, even worse. And 32,000 people a year die in the US. 1.2 million people die in automobile accidents worldwide, largely due to user error. And we can eliminate that by using these self-driving cars, and I think we will. We'll eventually look back and be thinking, what were we thinking? Driving cars. It's a robot's job. Here we have a bunch of students that are using the One Laptop per Child system. How many of you are familiar with that project? It's an old project that's now been superseded by new technology, and I'm using this slide for a reason. These note computers with Wi-Fi on them were delivered into places in the developing world that sometimes didn't even have access to internet or electricity. And they gave rise to Slate computers, and there's now a $35 Slate computer, like an iPad, and that is going to be distributed all over the world and give children access to both the internet and amazing educational capabilities. But what we're really after, even though we have systems like the Khan Academy, which you just were talking about before this talk, or Coursera or Udacity, lots of different systems that provide education on the web, most of these systems are not super individualized. And what AI can do is provide one tutor per child. One tutor per child or adult learner. That's what we want. We want that AI to model you, the user, model the domain, it might be calculus, and model the difference between what you know and what you need to know, and help you bridge that gap individually, at your pace. And do that in every subject area. This system is called Command Post of the Future. It's a portable command and control system built for the US military. Now, why am I showing you that? Aren't we interested in problem solving, solving grand challenge problems? And the answer is, yes, we are. And it's exactly this kind of capability that will help us in the next crisis, whether it's Fukushima, Japan, or New Orleans, in the States, or Chernobyl. Wherever we have a really serious crisis, we need systems that can give us situational assessment, logistics, basically command and control for dealing with crisis. AIs have been sponsored by corporations and governments all over the world. And why is that? Because of these sources of value added. If you could create a business, a startup, how many of you are interested in creating a startup or a business, doing something innovative? Raise your hand if you're interested in that. Well, take a look at this list. Augmenting skills, improving the accuracy of predictions, accelerating process timing, solving complex problems, improving quality, increasing productivity, decreasing cost, managing knowledge, and expanding the range of the possible. I mean, you can't find a list much better than that. And that describes the kind of value added that we find in AI applications over the last 25 years or so. And we're just getting started. We still don't have systems that have the broad, deep, and subtle intelligence that we associate with human intelligence, with our kind of intelligence. Is that the penultimate kind of intelligence? Probably not. But it does form a kind of benchmark, and we haven't gotten there yet. But we will, and we're going to get there in the not-too-distant future. So, one of the ways we'll get there is by using a lot of different sensor systems to understand how our own brains work. We're going to reverse engineer our own brains. Why is that? Because the brain is the best architecture for computing? No, but it has a proven architecture for our benchmark level of intelligence. So here we have an EEG system, electroencephalography, that measures weak electrical signals at the scalp. Or we can use functional magnetic resonance systems, where we put a person in a high-Gauss magnetic field and ask them to do different cognitive tasks, and then we measure where the blood flow goes in the brain, try to understand what parts of the brain are doing what kinds of problem solving. And we can use that information to create a variety of different maps about the brain. And why do we want to do this? This is a map of white matter in the brain that connects the thalamus with the cortex. Why do we want to do that? Because we want to emulate some of those circuits for ourselves. This guy is Dharmendra Mota at IBM Almaden, his friend, and he has been directing the Synapse project, which is a joint project of multiple institutions sponsored by IBM and DARPA. And Dharmendra has been building a neuromorphic chip, a chip that emulates synapses and the way synapses learn. So unlike our laptops, which use a von Neumann architecture that hasn't changed very much, even though we have multi-core architectures and larger caches and various improvements, they use a basic von Neumann architecture, and this system uses an architecture that's very much like the brain. The map that you see, the circular map here, is 383 different brain regions of a macaque monkey. And they also have, of course, at their disposal, all the maps that we've created thus far of the human brain. So we might ask the question, when we do eventually decode the human brain, will we stay within the confines of the human skull, which is largely limited by the mother's pelvis? I would suggest to you the answer to that is probably not. If you unravel the brain, the surface area of the brain is just a little bit bigger than a dinner napkin, a little bit bigger than this. And one could imagine creating an artificial neocortex that has the surface area of this stage. Or how about a surface area of this auditorium? Or Moscow? Or Russia? Or the Earth? Now, why do we want to create an artificial intelligence with that much computing power? What could we do with that kind of computing power? And the answer is we could look at and comprehend the accelerating wavefront of human knowledge. This is a diagram of citations in different areas of human knowledge. It's from the Public Library of Science. And you can see that any one person might master one particular discipline, like physical chemistry, and maybe child psychology, and economics up here. But no one person can comprehend the accelerated knowledge in all of these fields. But one could imagine an AI could do that, and the most interesting aspects of innovative work are often done at the edges, the interdisciplinary edges between fields. And that's why it would be really important to have powerful AIs. And we'll interact with them with very large and immersive environments, like this Hyperwall 2 system from NASA. It's 128 different displays, each one driven by its own supercomputer. And it could be one big display or individual displays. So we'll have lots of ways of getting the knowledge from these big systems into our heads. And we'll be able to, in fact, wrap sensors around the whole planet, billions of sensors, and use these big, powerful AIs to build predictive analytic systems and smart skins for our planet to help us manage the planet with greater effectiveness for storms and earthquakes and things like that.